while ago about these little guys. We've talked about the span of Earth history, and you've made timelines, and you kind of have a sense that there's been life on Earth for a long time. And we said about 300 million years ago, give or take, these little tiny mammal-y things showed up. They look kind of like modern shrews. When we go to the Carnegie in the spring, like I said, I'll give bonus points if you can find the little fossil mammal that's running around the dinosaur's feet. They're pointy-nosed and sharp-toothed, but they have fur, and they have nipples, and they give live birth, and they nurse their young. They're mammals. They are totally, clearly mammals. And they gave rise to other mammals eventually. It took a while. That's 300 million years ago. And eventually they give rise to some other mammals that look a little bit more like some of the ones that we know. Mammals like these guys in, 250 million years. And eventually these guys, about 1 million years ago, finally give rise to something that looks more like something we know pretty well. About 1 million years ago we have these beautiful folks. And then just in the last 20,000 years or so, we have something that's a lot more familiar to all of you. Aww. This is where you all go, aww. How can we tell that this is not the same as this? Okay, body size. That's a trait. You're saying that they differ in a trait. And we haven't seen one of these little tiny fossil mammals in here, but I told you they were pretty small. Now, are there small dogs? Yeah, my neighbor does rescue for she's always got extra little tiny dogs running around. It's crazy. Are there really big dogs? Yeah. So we can't rule out on size alone that this isn't a dog. How else is this thing different than a dog? The legs are different? Okay, what about them? They kind of look like the bones might be oriented differently. It's hard to tell. I mean, we're not looking at a full skeleton or anything. What are other things that might be different that might mean that this is not a dog? What do you think, Sage? Ah, so glad you said that. Nobody said that in the other class. Skulls. Skulls are a big distinguishing factor when you're looking at animals. Who here has ever found a skull in the woods? Okay. Because animals die in the woods. And they lay down and they rot. And if you get lucky, if you walk around in the woods long enough, you'll find bones. You might find bones on the roadside. Things get hit and their bones just lay there. And when you find a skull, you can actually get a key and you can tell what kind of animal that skull came from. So I have a little raccoon skull over here that a student brought me years ago. And you'll notice that there's a very distinctive pattern on the top of the skull. It looks almost like a little X. If you've ever found a fox or a coyote skull, they have a real big ridge down the middle of the skull. The shape of the eye sockets is very different. So if we looked at the skull of a dog and the skull of this little mammal, we would probably find some pretty big differences pretty fast. We know they're not the same species. But really, what makes them so different? It's their traits. And where that's going is the fact that we've said evolution, we've defined it a couple ways, that it's a change in heritable characteristics over many generations, that it's gradual change over many generations. It's biological change over time, and really, evolution is just a shift in the distribution of traits and the genes that cause them within a population. And the big idea is this, that accumulations of tiny differences can lead to major differences given enough time. Oops. When we look at any trait in any population of any species, most often if we look at a large enough sample, that trait will end up being a normal distribution, having a normal distribution, where we have the great middle average of everybody, where most people have their values. And then we have these little minorities out here. So we can look at that for height. I am 5 foot 5.5 inches tall. Taller if I stand on something. There are a lot of other women my height. I'm average height for an adult female in the U.S. There are lots of women who are 5'4" and 5'5" and 5'6". We're all in here. There are some women who are 5'7" and 5'8" and 5'9". There are a few women who are 6 feet tall. There are very few women who are more than 6 feet tall. The WNBA, those ladies do not exist here. They're all up here. There are a few women who are 5'3" and 5'2" and 5 foot. My mother is 4'11". She's teeny. I've called her a miniature mom my whole life. I was taller than her in 5th grade. She's tiny. We're like different species. But we're not. We're not. We're genetically related. So, do you know any 3 feet tall adults? Okay. Do 3 foot tall... No, most of you probably don't. A few of you might. Do adults whose full size is 3 feet tall exist? Yeah. There are medical... And typically it's a medical condition. Dwarfism commonly yields adults who are very short-statured. We've seen a lot more about people with dwarfism in the last years because there have been a few TV shows that prominently featured people who had medical dwarfism.
My mom watched that Little Woman LA.
My mom loved, what was it, Little People, Big World? She used to watch that one all the time. I don't even think that's on anymore. So, there are adults who are 3 feet tall. Are there adults who are 8 feet tall? Yeah. Now, again, just like someone who's 3 feet tall probably has a medical condition, because that's not within the range of average heights. That's pretty far out there. And dwarfism is a medical condition. It's genetic. The world record holder, and I meant to get a picture of him, the guy was 8'2" when he stopped growing in his 20s. He had a medical condition. He had a tumor on his pituitary gland. The pituitary gland sits in the center of your brain. It controls a lot of your growth hormone. And so his body was producing not only too much growth hormone, but it continued to produce it. Basically his body didn't respond to the signals that said, whoa, we're done here, thanks a lot. And he had a lot of problems because the human body doesn't do well at the extremes. So people with dwarfism tend to have some joint issues, they tend to have some bone issues. People at the other end of the spectrum also tend to have some medical issues, some complications. And I can't remember his name, Robert something, I think. And he died pretty young because the medical condition that had caused his exceptional growth also basically made him very fragile in some ways. But, was he up here on this end of the spectrum? Yeah, he was. But the great, vast majority of us are here in the middle. We're in the middle. Can traits shift in a population? Pardon? No? Okay. Did you ask something or say something? Okay. I do that all the time. Can traits shift in a population over time? How many of you have ever seen a historical suit of armor from the Middle Ages, like in a museum? Okay. Stand up, both of you who've seen one. You've seen one? Stand up. If you've seen a suit of armor, stand up. What has happened to human heights in the last couple hundred years? We're much taller than our ancestors. So, 1,000 years ago, a guy who was 5'6" might have been really tall.
How does that happen?
Oh, that's a fantastic question. That's a fantastic question. I was hoping somebody would ask that. So let's say we look at let's say that this is all humans and this is 5 foot, well, let's say this is 5 foot tall. And let's say this is all humans, well, no, we'll just leave it there. 5, 6, 8, 4, 3. Okay. So let's say 1,000 years ago, the average, no, I didn't draw that very well. Let's say the average for all humans was there 1,000 years ago. Then on average, most people were shorter. Is that possible? Yeah. It's factual, you know. Maybe somewhere between 4 and 5 feet tall was average for all humans 1,000 years ago. And over time, can average, shift? It can. What causes a shift like that? Well, there are 2 things that can cause it. There are 2 things that can cause it. What are the 2 sources of variation in any trait? This was on your quiz today. It was in your lab yesterday. What are the 2 sources of variation? Genetics and environment. Yeah, genetics and environment. So, there are 2 answers to how could this happen. Either one, genes that make people taller offered some advantage, and so tall people survived longer, had more babies, were more successful in general. That's possible. The other is environment. What feature of your environment kind of really controls whether or not you reach your height potential? Do you guys know this? Nutrition, calories. Yeah. So I don't know if you realize what a weird time we live in. How many of you have ever been to a grocery store? What are grocery stores full of? Food. Realize that for most of human history, no such thing existed. Realize that for most of human history, every single thing that you ever ate, you either killed or grew or found yourself out in the world. How many of you have found something in the wild, whether it's shooting a squirrel, taking a deer, picking wild berries? How many of you have picked food in the wild and eaten it? Harvested food in the wild and eaten it? Awesome! This is why I teach where I do. Because I could walk into a high school in suburban America and everybody would be like, what? Okay, for most of human history, it was totally on the humans to go out and find what you could eat. The concept of being able to walk into one place and just have your pick of food is unheard of. So 1,000 years ago, a lot fewer people had enough calories on a regular basis. And not getting enough calories on a regular basis, especially when you're a child, tends to mean you don't reach your full height potential. So that's part of it. And they talk about like European immigrants in the late 19th, early 20th century. A lot of those folks were coming from, varying levels of poverty in Europe to sort of this, whether imagined or not, land of plenty. And their kids tended to be taller than the parents, reliably. How many of you are taller than your parents? Okay, me too. By far, by a head. Okay, so that was a great question, because what we want to think about is the fact that traits can shift in a population over time. Well, actually, when traits in a population shift over time, that's evolution. Are humans evolving to be taller? Yes. Over the last 1,000 years, humans have evolved to be, on average, taller than their ancestors. That's evolution in a nutshell. So let's look at some other ways that a trait can be distributed. And these are a couple sections of notes that mean nothing if you don't have pictures with them. And I'm glad to see some of you are now using notes to do pictures. Good deal. Awesome. Evolution changes the distribution of traits and the genes that cause those traits. So we have 2 distributions here that are what we call skewed. They are skewed. And if you take probability and data analysis with Mr. Andres, has anybody had that class? A lot of people take it their senior year. It's pretty easy math. It's kind of a fun math. It's a good practical math. He talks a lot about distributions and about skewedness, and you can have right and left skews, or they can be called positive and negative skews. But basically it means that you have more folks at one end than you do in the middle. So we could also talk about a downward skew or an upward skew. You know, a downward skew would mean you have more people at the bottom, at the lower end of the value. In a skewed distribution. Now, what is the mode again? Do you remember? Mode is... It's the measurement that occurs most often. And if we look at a graph of a distribution, the mode is the high point. So, for instance, in this one, here's the mode, somewhere in here. And you can probably expect a test or a quiz question that says, you know, identify the mode on this distribution. So, did anybody here have a data set for their trait that had 2 modes? You did? Okay. In the other class, I know we had one group that had a trait that had 2 modes. What prefix means 2? Bi. Hey, guess what this is? It is a bimodal distribution. Guess where the modes are? Right here and right here. A bimodal distribution has 2 modes. So when we think about a trait becoming more, so let's think about what happened. I'll let you guys finish this and then we'll go back to another graphic. So if we think about shifting populations, I should make that another color so it shows up better. Is that better? And we say that, well, you know, 1,000 years ago, average humans were shorter than they are now. Maybe the average was just over 4 feet. If we count in men and women, all adults. And then, you know, by this time, the average for all adults might be here. In between those 2 distributions, there may have been a skewed distribution. Very often we go from something that looks like this to something that looks like this, and then it all kind of levels back out. And we have sort of a new normal. So distributions do shift over time, and that's evolution. Now, how the trait is distributed shifts. The other thing that can shift, whoops, I'm sorry. What did we say can cause a change in height? Yeah, either your environment, and for the most part with height, it's really how many calories you get and what kind of calories you get. Getting good nutrition. What else? Genetics, your parents, yeah. I used to work with a woman who was 6 foot tall. Her husband was 6'1". She had 2 sons who were 6'1" and 6'2". She was one of 6 siblings from a dairy farm in Carrollton. All of her siblings were over 6 feet tall. All of their kids were 6-footers. I mean, it was just a crazy tall, they were all like tall, blonde, like, I don't know, they looked like I don't know what they looked like. They looked like a bunch of tall, blonde people. And I mean, girls, boys, every single one of them was 6 feet tall. They were just incredibly tall. And she said, yeah, you know, like, her parents had built their farmhouse, and she said, other people think our house is strange. The doors are all higher. They had literally, because they built it, in the 40s, just working on their own, and the cabinets were all up higher, and the door frames were all a little bit higher, because everybody in their darn family is 6 feet or better. So it was a big house. If you were 3 feet tall and you were building your own house, like some of those shows with people who have dwarfism, they build their houses much smaller to accommodate themselves. So yeah, your environment can change a characteristic, and your genetics can change a characteristic. If we think about the genetic sources of that variation, there's another way to think about how something is distributed in a population, and it's called gene frequency. So gene frequency is what percentage of the population carries some gene.